Lecture 23 covers section 7.2.1. At the end of today's lecture, you should be able to analyze trusses using the method of joints. To employ the method of joints, we first must construct a global free body diagram of our truss structure to determine our reactionary forces. For instance, given the truss bridge as shown below, we'd apply our reactionary forces at pin A, RAX and RAY, and then a reactionary force at the roller, RBY. And we can use a global free body diagram, i.e. the summation of forces in the x direction, the y direction, and moments about a point to determine RAX, RAY, and RBY. Then we will consider component-wise free body diagrams of each pins, and we will assume each pin is under compression, and we'll construct equilibrium of force equations describing said pins. For instance, if we look at pin A, we'd have RAX and RAY provided from our global free body diagram, then we'd have RAB, which is a compressive force exerted by member AB onto our pin, and RAC, which is a compressive force exerted by member AC onto pin A. Then we will continue through our truss, analyzing each pin. For instance, we can look at pin B, where we'd have RAB, RBC, and RBD acting on that pin due to forces of members AB, BC, and BD. Now, we will continue through this process and solve for our forces acting on the pins via back substitution or by creating a system of equations. In example 1, we are considering a simple truss as shown below. We want to determine the forces existing within each member. For our truss, we have 2,000 newtons acting at pin A and 1,000 newtons acting at pin B. Pin C is supported by a pin support, and pin E is supported by roller support. Our geometry is shown as below. To begin, we'll start with a global free body diagram, and we'll apply our equilibrium equations. First, we'll start with the summation of forces in the x direction, and we find our reactionary force at C in the x direction, RCX, is equal to 0. Next, we'll apply our summation of moments about point C. We recognize our 2,000 Newton and 1,000 Newton force are going to create a tendency for our body to rotate counterclockwise, where REY is going to cause a clockwise rotation. Thus, our 2,000 Newton force is acting on a moment arm of 24 meters, and our 1,000 Newton force is acting on a moment arm of 12 meters. And we are going to subtract REY that's acting on a moment arm of 6 meters. We find REY to be equal to 10,000 newtons. Lastly, we can take the summation of forces in the y direction. We'd have minus 3,000 newtons acting due to our applied loading, and 10,000 newtons acting in our positive y direction due to REY. Thus, we can solve for RCY, the reactionary force at our pin joint. And we find RCY is equal to minus 7,000 newtons. Now that we have our reactionary forces, we can begin to analyze each pin individually. We will start by analyzing pin A. At pin A, we have 2,000 newtons acting downward. We have FAB acting in the negative x direction. We have FAD acting in the negative x direction and positive y direction. We will begin by taking the summation of forces in the y direction. We see we have FAD, which has to be multiplied by sine of theta, where theta is the angle between member AB and AD. Now, using a force triangle, sine of theta is simply equal to 8.00 meters per 10.00 meters. Thus, we'd have FAD times 0.800 is equal to 2,000 newtons, or we find FAD to be equal to 2,500 newtons. The positive sign of this force indicates our member is under compression. Then we can analyze the summation of forces in the x direction. We'd have FAB plus FAD times cosine of our angle. Cosine of our angle is simply 6.00 meters per 10.00 meters. The minus sign associated with FAB and FAD are neglected, for they are both acting in the negative x direction, and we have no force acting in the positive x direction. The sum of these two forces is equal to 0. Thus, we find FAB is equal to minus FAD times 0.600, or FAB is equal to minus 1,500 newtons. The minus sign indicates this member is in tension. Next, we can progress to pin D. We'd have FAD, FBD, and FDE acting on the pin. If we take the summation of forces in the y direction, we'd have FAD plus FBD, and both are multiplied by sine of the angle, which we found to be 8.00 meters per 10.00 meters. Thus, we'd have FBD is equal to minus FAD, and FBD is equal to minus 2,500 newtons. With that information, we are able to do the summation of forces in the x direction. In doing such, we'd have FAD times cosine of theta, where the quantity cosine of theta is equal to 0.600, and this is equal to FBD times cosine theta plus FDE. Thus, solving for FDE, we'd have FAD minus FBD times 0.600. Thus, FDE is equal to 5,000 newtons times 0.600, which is equal to 3,000 newtons. Moving to pin B, we recognize that we have FAB, FBD, FBE, and FBC acting on the pin, as well as an applied force of 1,000 newtons. We'll start by taking the summation of forces in the y direction. We'd have FBD plus FBE times sine of theta, and this is equal to 1,000 newtons. Sine of theta is equal to 0.800. Thus, FBE is equal to 1,250 minus FBD units of newtons, or FBE is equal to 3,750 newtons. With FBE, we can solve the summation of forces in the x direction. We would have FAB plus FBD times cosine of theta, and this is equal to FBC plus FBE times cosine of theta. Thus, solving for FBC, the only unknown remaining in our system, we'd have FAB plus the quantity FBD minus FBE times 0.600, and this is equal to minus 5,250 newtons. Next, we can move to pin E. At pin E, we have FDE, FBE, FEC, and REY acting on it. If we take the summation of forces in the x direction, we'd have FDE plus FBE times cosine theta, and this is equal to FEC times cosine theta. Thus, FEC is equal to FDE per 0.600 plus FBE, and we find FEC being equal to 8,750 newtons. As a continuity check, we'll do the summation of forces in our y direction, where we'd have FBE plus FEC, this quantity times sine of theta, and this has to be equal to 10,000. This equation is satisfied once we substitute in our known values. Thus, we have all our forces of the members known, and we don't have to analyze pin C.